Right now, while you watch this video, something almost impossible is happening. Millions of tiny messages are racing beneath oceans, through the walls of your home, and across the sky, and nearly every single one of them arrives. This is the story of how the internet actually works. Not the cartoon version, the real one. Let's start with a simple question. This video is stored on a server, a computer that might be sitting 10,000 kilometers away from you. Between your device and that machine, there is no single cable, no direct line, nothing that was reserved just for you. And yet, the video plays. To stream it smoothly, that server has to deliver millions of bits to your screen every single second. Each bit crosses continents, passes through dozens of machines owned by different companies in different countries, and still shows up on time, in order, intact. How is that even possible? And here's the weird part. Nobody is in charge. There is no central computer directing traffic, no company that runs the internet, no master switchboard. It is a swarm of independent networks that only agree on one thing, a common set of rules. Break the problem down, and each piece is surprisingly simple. So in the next 15 minutes, we're going to follow one message all the way down and back up. For big ideas. First, signals, how bits physically move. Second, packets, why data gets chopped into pieces. Third, routing, how a path is found across the planet. And fourth, TCP, how reliability is built on top of chaos. Part 1. Strip away every app, every website, every protocol, and the internet is doing exactly one thing, moving ones and zeros from one place to another. That's it. Every photo, every message, every video, including this one, is just an enormous list of bits. So the first problem is brutally physical. How do you move a bit? On a copper wire, a 1 can be a burst of voltage and a 0 can be its absence. Watch the wire for a fixed slice of time. Voltage high, that's a 1. Voltage low, that's a 0. Do this a billion times per second, and you have gigabit networking. The bits you saw above become this electrical waveform. But copper is only one carrier. Over long distances, the internet prefers glass, fiber optic cables, where a 1 is a flash of laser light, and a 0 is darkness. And through the air, your Wi-Fi and mobile data encode those same bits as radio waves. 3 different physics, one identical idea. Fiber is the true backbone of the internet. Inside a strand of glass thinner than a human hair, light bounces along at about 200,000 kilometers per second, crossing the Atlantic in under 30 milliseconds. There are over 1 million kilometers of these cables lying on the ocean floor right now. Of course, real signals fade. Voltage sags, light dims, radio drowns in noise. So every few dozen kilometers, repeaters read the weakening signal and re-emit it fresh and clean. Because the signal is digital, just ones and zeros, it can be restored perfectly every time. This is why a bit can cross the planet without a single error. 2 numbers describe any of these pipes, and people constantly confuse them. Bandwidth is how many bits you can push per second, the width of the road. Latency is how long one bit takes to arrive, the length of the road. A truck full of hard drives has astronomical bandwidth and terrible latency. A gaming connection needs the opposite. The internet has to serve both. And latency has a hard floor, the speed of light. Light in fiber covers about 200 kilometers per millisecond. So from Europe to America and back, physics alone costs you roughly 80 milliseconds. No engineering can ever beat that. This single constraint shapes the whole internet. It's why big services copy their data into hundreds of cities, so the answer is never far from you. So that's layer 1 of the internet, an ocean of copper, glass, and radio that does nothing but move raw bits between neighboring machines. It doesn't know what a website is. It doesn't know what a video is. And that ignorance is a feature, because everything else is built as layers on top of this one dumb, fast pipe. Part 2. Packets. Here's a puzzle. Suppose you want to send a 2 gigabyte movie to a friend. The naive approach is obvious. Open a connection and push the whole file through as one giant, continuous stream of bits. Simple. And for the internet, completely unworkable. Why? Because wires are shared. If your movie occupied a cable as one unbroken stream, everyone else's data would have to wait in line behind all 2 gigabytes of it. Someone's video call would freeze for minutes. The early network engineers of the 1960s saw this problem clearly. You cannot let anyone hog the road. So the internet does something smarter. Every message, no matter how big, is chopped into small pieces called packets, each around 1,500 bytes. Your 2 gigabyte movie becomes roughly 1.4 million little packets, and they all take turns on the wire with everybody else's packets. The road is shared millisecond by millisecond. Now, every packet has to survive on its own, so each one is wrapped like an envelope. At the front, there's a header, the sender's address, the destination address, and a sequence number saying which piece of the message this is. After that comes the payload, the actual slice of your data. And this is where it gets interesting. Once released into the network, packets are independent. 2 packets from the same message can take completely different roads across the planet, depending on which links are busy at that instant. Watch, same message, 2 different paths at the same time. Different roads have different lengths, so packets routinely arrive out of order. Piece 3 shows up before piece 1. That's fine. Remember the sequence numbers in the headers? The receiving computer uses them to put everything back in order, like numbered pages of a shuffled book. But here's the uncomfortable truth at the heart of the internet. Packets can simply vanish. A router's queue overflows, a radio link glitches, and the packet is gone. No error message, no apology. The core network promises almost nothing. It's called best effort delivery, and everything that feels reliable about the internet is built on top of this unreliable foundation. Remember that. It becomes important in part 4. By the way, that packet size, roughly 1,500 bytes, isn't arbitrary. It's a compromise engraved into Ethernet in the 1980s. Bigger packets waste less space on headers, but they hog the wire longer and lose more data when one is corrupted. 1,500 bytes was the sweet spot, and 40 years later, almost every packet on Earth still respects it. Part 3. Routing. For a packet to travel anywhere, machines need addresses. Every device on the internet gets an IP address. On screen is a real one. It looks like 4 numbers, and that's exactly what it is. 4 bytes, 32 bits, a coordinate in the address space of the entire internet. Your phone has one. The server has one. And the magic question is, given only a destination address, how does a packet find its way across an unmapped planet-sized web of cables? Nobody hands it a route. There is no global map. The answer is one of the most elegant ideas in computer science. Between you and any server stand routers, specialized computers whose only job is passing packets along. Here's a tiny piece of the internet. 6 routers connected in a mesh. Notice there are many possible paths from left to right. That redundancy is deliberate. It's what lets the internet survive cut cables and dead machines. Now here's the part most people get wrong. A router does not know the whole internet. It keeps a small table that says, roughly, for addresses starting with this prefix, hand the packet to that neighbor. That's all. A handful of rules, covering millions of destinations by their prefixes. So a packet's journey is just a chain of tiny local decisions. Your packet reaches router 1. Router 1 looks at the destination, checks its table, forwards to router 2. Router 2 does the same and picks router 3. No single machine ever sees the whole path, and yet, hop by hop, the packet crosses the world. A typical journey takes 10 to 15 hops. You can actually watch this happen on your own computer with a tool called traceroute. It reveals every router your packets pass through, across your city, into a national backbone, through an exchange point, maybe under an ocean, and finally into a data center. And because every router decides locally, the network heals itself. In 2006, an earthquake snapped 7 submarine cables near Taiwan. Within minutes, routers around the Pacific noticed dead links, updated their tables, and traffic simply flowed around the damage. Longer paths, slower, but alive. No emergency meeting, no operator flipping switches. The rerouting is automatic. and it happens somewhere on Earth every single day. Zoom out far enough, and the internet is not one network at all. It's about 70,000 independent networks, internet service providers, universities, tech giants, each announcing to its neighbors, "Here are the addresses I can deliver to." A protocol called BGP spreads those announcements around the world. The internet, literally, is networks agreeing to carry each other's traffic. Part 4. Let's take stock. We can move bits physically. We can chop data into packets and route them across the world. But remember the fine print. Packets can vanish, duplicate, or arrive out of order. Streaming a video over that raw service would be chaos. What we want is a clean promise. Every byte arrives, exactly once, in order. That promise is delivered by TCP, the Transmission Control Protocol, designed in the 1970s by Vint Cerf and Bob Kahn, and still carrying most of the internet today. The trick? The network stays dumb and unreliable. All the intelligence lives at the two endpoints, your device and the server, cooperating through a clever set of rules. It starts with a handshake. Your device says, "SYN, I'd like to talk, and here's my starting sequence number." The server replies, "SYN ACK, got it, here's mine." You answer ACK, confirmed. 3 messages. And now both sides are synchronized and ready to count every single byte that follows. Then data flows, and everything is numbered. Every packet carries sequence numbers, and every time the receiver gets data, it sends back a tiny acknowledgement, an ACK saying how far it has gotten. The sender is never guessing. It knows exactly which bytes made it, and which are still in flight. Now watch what happens when the network misbehaves. Packet 4 is sent and lost. The ACKs stop advancing. The sender waits, a couple hundred milliseconds, hears nothing about packet 4, and simply sends it again. This time it arrives. The ACKs jump forward, and the stream continues as if nothing happened. Loss becomes a non-event. There's one more subtlety. How much data should be in flight at once? Send one packet at a time, and you waste the network's capacity. Send everything at once, and you flood it. So TCP keeps a window, a budget of unacknowledged data, sliding forward over the stream as ACKs come in. And that window is how the internet avoids collapsing. TCP starts small and doubles the window every round trip, slow start, until it senses loss, which means some router is overflowing. It backs off, then probes forward again, endlessly hunting for the fair share of the network. Millions of TCP connections do this dance every second, without ever talking to each other. Not everything wants this machinery, by the way. A video call would rather skip a lost frame than pause to resend it. Yesterday's audio is worthless. For those cases, there's UDP, TCP's minimalist sibling. No handshake, no ACKs, no ordering. Just packets thrown at the destination. Games, calls, and DNS lookups live on UDP. The lesson: reliability is a choice, and it has a price, latency. Step back and admire what just happened. Out of a network that promises nothing, a few rules running on the two endpoints create a perfect illusion, a smooth, ordered, reliable pipe between any two computers on Earth. That illusion is what every app you use is built on. Part 5. Let's put the entire machine together and follow one real request. You type a website's name and press enter. First problem: names aren't addresses. So your device asks the domain name system, a global, distributed phone book, and gets back the server's IP address in a few milliseconds. Next, the TCP handshake you just saw, 3 packets exchanged with the server. Then your actual request rides across the chain, from your device to your Wi-Fi router, into your ISP, onto the backbone, maybe through a submarine cable, and into a data center where the server lives. The server replies, and the response, this very video, is chopped into packets that pour back along the path, each one addressed, routed hop by hop, acknowledged, resent if lost, and reassembled in order on your device. Millions of packets, flowing every second, just for you. One more layer rides on top of all this: encryption. Before any real data moves, your device and the server run the TLS handshake, agreeing on keys that scramble every packet's payload. Routers along the way still read the addresses. They have to deliver, but the contents are mathematically sealed. That's the padlock in your browser. Total time for the first byte to appear? Often around 100 milliseconds. In a tenth of a second, your request touched dozens of machines, crossed multiple networks owned by different companies, and triggered thousands of routing decisions. All of it invisible. All of it running on the ideas you now understand. So here's the internet in one breath. Physical signals carry raw bits. Data is chopped into independent packets. Routers forward each packet with small local decisions. And TCP, running only at the edges, turns all that chaos into a reliable stream. 4 ideas, stacked into the most transformative machine humans have ever built. And maybe the deepest lesson, nobody controls it, yet it works, because good rules beat central control. Next time a page loads instantly, take half a second to appreciate the swarm of tiny, careful decisions that made it happen. If you enjoyed this journey, stick around. There's a lot more of the invisible world of computing to explore.